Okay, now today let us consider the another type of the microwave tube. So that is a two cavity klystron. So this two cavity klystron is used as an amplifiers. Okay. So as the basic purpose of this particular tube is to amplify the microwave signals. So the amplification, why you need an amplifier and amplification processes, as you have studied in your lower semesters, we are using the different types of the amplifiers, RC coupled amplifier, LC coupled amplifiers to increase the strength of the signals. And here also, so to increase the strength of the high frequency signals, we are using this two cavity klystron amplifiers. Now, if you look into the construction details of this one, so the basic construction details of this particular device is similar to the previous klystron oscillators. See here, here you have a cathode and you have heating elements, and then you have a cavities. But in this particular case, we are having two cavities. So therefore, this particular device is called as a two cavity klystron devices. In the previous one, in the reference klystron, we are having only one cavities, but here we are having the two cavities. Now, so the basic functional difference between this and the klystron amplifier is that here we are using the two cavities, and apart from this, here at this particular place, if you observe here you are having the focusing electrodes. So this particular focusing electrode is not present in the klystron oscillators. And the basic on which this particular device operates is same as the previous one, the klystron oscillators. This particular device functions. Now, here when you apply voltages, so this particular heating element start heating, so this heat energy will be transferred to the cathodes. When the cathode gets heated, then the electrons start emitted. Okay. So whatever the electrons are start emitting, so these electrons will move towards this particular catcher cavities. Okay. Before they reach to this particular catcher cavity, so they have to pass through this particular buncher cavity. You are having an RF input. So that RF input, that is the radio frequency signals, whose signal strength you want to amplify, are the signals which you want to amplify. So that is given to as an RF input through this particular coaxial cable here. And so the amplified output signals from this particular two cavity klystron amplifiers is taken through this particular coaxial cable as an RF output at the catcher cavities. And then, so here, here you are having a buncher cavity, and here you are having a catcher cavities, and the space between, so this particular buncher cavity and the catcher cavity is known as a drift space. Okay. And here, so whatever this particular square blocks, boxes have been shown, rectangular boxes have been shown. So these are nothing but the bunched electrons. Okay. What is meant by this bunching? In the previous class we have seen the things. The same bunching process takes place here. These bunched electrons will move here. Second next is coming to the construction details in this. Here the question occurs is that why this particular focusing electrodes are to be used in the two cavity klystron oscillators. So the basic function of this particular focusing oscillator is to focus the electrons to a particular point. Okay, what is happening in this particular case is that when the electrons are emitted from this particular cathodes, so there is a possibility that some of the electrons which are emitted from this particular cathode will get deviated from that particular path. Now our purpose is whatever the electrons which are emitted from this particular cathode, whatever it is here, so these electrons, instead of deflecting from their particular path, all the electrons have to be focused toward a particular path. So for this particular purposes, here we are using these particular focusing electrodes. And now see here, so for this particular focusing electrodes, we are applying this particular negative voltage. See here, so this is the negative voltage applied to this particular focusing. Now when you apply the negative voltage here, and the electrons are negatively charged particles, and this potential applied to this electrodes is also negatively charged particles. Even if any of the electrons move toward this particular focusing electrode or move toward this particular focusing electrode, what they will do? Because the charge of that particular electrode is also negative, and the electrons they will repel. Okay, that is the case is that even though some of the electrons are get deviating from the path because of this focusing electrodes, so negative polarity they will reflect so that your electrons will be focused to a particular point. That is, once again I am telling you, so these particular focusing electrodes are used to focus all the electrons which are emitted from this particular cathode to a particular point, because our purpose in the reflection. So let us see how this particular bunching takes place. Now, as we have seen in the reflex clusters, here also. So this is just the diagram is Applegate diagram is shown for the 3 electrons. Okay, the same effect what it has been shown for the 3 electrons, the same effect will be there for all the n number of electrons. Now, as it has been told in the previous class, this is the electrons which is entering, and this is the another electron which is entering, and this is the another electron which is entering. Closely if you look into this, so depending upon across which potential, so these electrons are occurring. If the electrons are occurring with a neutral potential, then these electrons through this particular gap will passes through the same velocity. If the electrons occurs with a negative potential field, a negative field potential, then it passes with a lesser velocity, and if the electrons occurs in the field with a positive field, so the electron velocity get increases. If this is the case is there, what happens is that even some of the electrons which are entered first, some of the electrons which are entered late, but depending upon the field potential, all the electrons will come out of this particular bunch air cavity with the same amount of time, and here so bunched electrons we are getting, and these bunched electrons will move toward this particular catcher cavities. Okay, when they will move toward this particular catcher cavities, so what the thing is happening is that whatever the energy, okay, they got from at the bunching process, so they will transfer this particular energy to the whatever the field is present in this particular catcher cavity. I am telling you once again. All the bunched electrons which are moving toward the catcher cavity. Okay, so this when all the bunched electrons when they move toward the catcher cavity, so then this we are calling it as a current modulations. And all these bunched electrons move toward the particular catcher cavity. So what they will do is that whatever the energy they got, okay, though they will transfer this particular energy to the catcher field. When they transfer this energy to the particular catcher field, then here the amplification signal strength will be get increased. One more the factor you have to remember here is that we will get a maximum amplification when the losses occurs in this particular tube is more than the energy transferred by these particular electrons. Remember one thing, so always in any device certain losses are there, okay, and here also certain losses are there, but to overcome that particular loss, okay, so these bunched electrons will transfer the particular energy. As the energy transferred by these particular electrons is same as losses occurring in these particular things, then there is no amplifications. But now here what is happening is that as n thousands of lakhs of electrons are moving and they are bunched together, and they will transfer that particular energy. And when they transfer that particular energy, it is automatically more than, so whatever the energy loss occurring in this particular tube. So therefore, so the signal amplified values will be catched from this particular catcher, because we are catching the signals. Okay, that means whatever the energy will be transferred from this electrode to this particular field, so that energy will be converted into electrical energy. So this energy will be taken by this particular catcher cavity. So therefore, it is called as a catcher cavity, and this energy will be taken through this particular coaxial cable or any type of the micro device, so which will can carry these particular signals. Here we are getting the output, and here, so this is called as a bunch air cavity, because here the electrons are bunched together, and in this particular space we are having a drift space. So the drift space is the one where, so here the electrons are moving with the uniform velocity, but in the gap, in the cavity gap, the electrons are not moving with the uniform velocity, because so depending upon what potential is there in this particular gap, positive, negative or the neutral potential. Accordingly, its velocity gets changes. But when they come out of this particular cavity gap, in the drift space, all the electrons are moving with the equal velocity. So this is how this particular two cavity klystron device can be used for the amplification purposes. And so as I have told you that the electrons are moving, so they are bunched together and they are catched together. So the same diagram it has been shown in this. Here from the cathode the electrons are moving, okay, and in the bunched cavities, so the electrons are bunched together. So you can observe it here. See that these are the dots what have been shown here. So these are not the single electrons, so these are the bunched electrons. Okay, bunched electrons means in the single dot you may be having thousands of electrons. Now, so these bunched electrons will move toward the catcher cavity. Just recall your memory of the previous diagram. You have a buncher cavity and you have a catcher cavity. Okay. Now, from the buncher cavity, here the electrons are coming normally in the buncher cavity. So they will form a bunches, and these are the bunched electrons. So these bunched electrons will move toward the catcher cavity, and these bunched electrons will be collected by in this particular catch. And as you know, the flow of electrons is nothing but the current. Now, as here, more number of bunched electrons, okay, more number of bunched electrons will be collected by this particular catcher cavity. Automatically, the whatever the RF signal what you want to amplify, so it will be get amplified. Okay. Now, this is the diagram, just one more illustration of, okay, it is just an illustration of how that amplification will take place. You see here, so this is the cathode emits the electrons, and this is the buncher and the catcher cavity. These are all the diagrams. What I am showing you is that in order to have a better understanding of how this particular two cavity klystron works. As you can see here, so this value what it is showing here, what it is at. Now, what is your amplification? Increasing in the strength of the signals. Okay. Here, imagine the case just as an illustration. Here, what is happening is that your signal strength is low, but as you can say that it is increasing. It is nothing but comparatively I am telling you. Now, here what is happening is that when the electrons are emptied from this one, so the density of the electron goes on increases. How the density of the electron goes on increases is the bunching of the electron goes on increases. Okay. As the density of the electron goes on increases and the number of electrons flowing per second goes on increases. What is current? The flow of electrons. Okay. When the less number of electrons are flowing, less number of current will be there. When more number of electrons is flowing, more number of amount of the current is here. Here, as the density of the electrons is increasing, automatically the amount of number of electrons flowing per second is increasing, automatically the signal strength is increasing, automatically we are getting the amplification. So this more density electrons will be catched by this particular cavities, and so when catched by this particular cavities, here we are getting the amplified version, okay, of the signal, RF signal, which you apply at the input side. Okay. So this is in this particular diagram, this is just an one more enhanced diagram of this particular bunching process in the buncher cavities. As you can see here, so this is one bunched electrons. So this is one bunched electrons. So like this, thousands of lakhs of bunched electrons will be there. So that you can just simply I will show it here. See it here. So this is one bunched electron. This is, don't consider that it is a single electrons. Here thousands of lakhs of electrons are bunched together. So these are the bunched electrons. So how this particular bunching process takes place will be shown with the single. So here the electrons are bunched. Here what it is showing is that only 3 electrons are bunched. Okay, don't think that only 3 electrons, but just it is for the illustration purposes. Along with this one, hundreds of thousands of electrons are moving and they are bunched together as a single dot. Such single dots, okay, such single dots are shown at this particular point, and these bunched electrons are moving. Okay. Now, next is one more diagram in order to give the better understanding of this particular concept. So here, so in this particular diagram, just I have shown only 3 electrons, and here we have shown only 2 bunches. Now if you observe this particular diagram, you can observe here n number of electrons are moving and forming a bunch, n number of electrons are moving and they are forming a bunches. Okay. Now such diagrams what we are doing using to illustrate the bunching process, it is called as an Applegate diagram. Okay. And now the characteristic of this particular device is efficiency is about 40%, and peak output power generated is up to 30 megawatts, and the average output power is up to 700 kilowatts, and it is at a frequency of 10 gigahertz, and power gain is about 30 dBs, and bandwidth is ranging from 1 to 8%. After studying the Ripples clusters and the 2 cavity clusters, now let us see the multi-cavity clusters. What is meant by this multi-cavity clusters and why you are using this multi-cavity clusters. Now, as you studied in the 2 cavity clusters, is basically used for the amplification of the RF signals. But if you use a single 2 cavity cluster, the amplification what you are getting or the gain what you are getting, sometimes it may not be sufficient to meet the application requirements. We want to increase the gain. So for that particular purposes, we are using this particular multi-cavity clusters. Now as you know, in normal amplifiers, if the gain is not satisfactory, then you are going for the multi-stage cascading of the amplifiers. 2 stage, 3 stage, 4 stage, 5 stage amplifiers we are using in order to increase the gain. Similarly here also, in order to increase the gain, okay, then we are going for this multi-cavity clusters. So here you can see here, so this is one cavity, so this is another cavity and this is another cavity. Like this here only the 3 cavities have been shown. Like this n number of cavities are there. Okay, and this is one the construction details is same as the previous one. Here you are having the anode and here you are having the collectors. 2 cavity cluster we are having only 2 cavities, and here we are having the n number of cavities. Okay, and this is the space what you are having. It is the drift space between these 2 cavities, and this is the drift space between these 2 cavities. Now let us see how this particular 2 cavity cluster works. Okay. Now for simple understanding purposes, let us consider the multi-cavity cluster, that is the 3 cavity clusters. Here the 3 cavities have been shown. Now the signal in the first gap results in small bunching of the electrons. Okay, the signal in the first gap results in a small bunching of electrons, means so from this cavity to this particular cavity, this is the first cavity, this is the second cavity, and this is the last cavity. Okay, now so this is the cathode and this is the collectors. Now the cathode when the cathode gets heated, it starts emptying the electrons, and these electrons will move from this particular cavity to this particular cavities. The signal in the first gap results in a small bunching of, here a small bunching of electrons will take place. Then the voltage in the second gap is much greater than in the first one. Then the voltage in the second one is much greater than the first one. Then the bunched beam enters the third gap and produces the large amount of the things. You need to see that here some amount of the amplification will take place, and here some amount of amplification will take place, and here some amount of the amplification will take place. That means to say that as the electrons are going on moving from one cavity to the other cavities, okay, so the value of voltage goes on increases. That is, voltage in the second gap is much greater than the first one. Whatever the voltage you are having at this particular point, so this voltage is more than this, and the voltage you are having at this point is more than this. If you are using few more stages, then the voltage goes on increases. 3 cavity cluster can also be used as a self-excited oscillators. Okay, and the power is fed back from the second cavity to the first cavity. So whatever the power is generated from the second cavity, it is fed to the first cavities, and the first 2 cavities determine the frequency, and the third cavity is responsible for the power amplifications. Okay, for the 3-stage klystron is considered. Okay, the power is fed from the second cavity to the first cavities, first one. Next is the first 2 cavities determine the frequency, and the third cavity is responsible for the amplifications. That means these 2 cavities will determine so what frequency you want to generate it, and this cavity will determine so what is the amplification you are supposed to get it. And if you want to use you want to get more amount of the amplifications, so then we are increasing the number of cavities. So let us consider some of the mathematical equations which are used for the analysis of these 2 cavity klystron amplifiers. For the velocity modulations, we are coming across the different types of the equations. So then for the calculation of the velocity modulations, first you have to calculate so the average electron velocity, and the average electron velocity is calculated u of AV is equal to u0 into 1 plus beta 1 into v divided by 2v0 into sine of omega t1 plus theta g divided by 2. And since v1 is always less than v0 and using binomial expressions, so these equations I will simplify to a u of AV. So that means to say that the average velocity of the electrons will be calculated from the equation uAV equal to u0 into 1 plus m by 2 into sine of omega t1 into theta g by 2. Where in this particular equation, whatever the m is there, so m is called as or known as the depth of modulations, and this m is calculated from m is equal to beta 1 into v divided by v0. And to solve the problems for the 2 cavity reflex klystons, you have to remember so this equation, that is u0 equal to u0 into 1 plus m by 2 sine of omega t1 plus theta g by 2. In this m is equal to beta 1 into v divided by v0, where m is called as a depth of the modulations. And the exit velocity of the electrons from the bunch-air cavity, okay, so is calculated from the equation u0 at t2 equal to u0 into 1 plus m by 2 sine of omega t2 minus theta g divided by 2. Okay. Then the transit time in the drift space, okay, that is the in the drift space is nothing but the space between the bunch-air cavity and the catch-air cavity, and the transit time in the drift space is indicating that how much amount of the time the electrons will take to move from a bunch-air cavity to the catch-air cavity. Okay. The transit time in the drift space is represented by Td. Okay. The transit time Td in the drift space is calculated from L divided by u0 into 1 minus m by 2 into sine of omega t2 minus theta g, so divided by 2. So this equation is used to calculate that drift space transit time. Okay, now let us consider the density modulations. Now because of the difference in velocities of the electrons in velocity modulation beam, the electrons form a bunch, because in the function of this particular 2 cavity klystrons, we have seen that how the bunching takes place. This bunching takes place because of the difference in the velocities, and because of this it becomes a density modulated. Now in the bunching process, we have seen that there are 3 types of the velocities you will get. One is the no velocity, change in the velocity, another one is the with the increase in the velocity, and another one is the decrease in the velocities. And u0 is nothing but unchanged velocity is u0. This is the velocity you are getting when the electrons come across the neutral potentials, and u minimum is the velocity you are coming across when the gap voltage is having a negative potentials, and u maximum you are getting so when the gap voltage is having a positive potentials. And the maximum degree of bunching takes place when the buncher and the cavities are spaced to satisfy. That means bunching, we want to have a maximum bunching to takes place, and the more number of electrons are to be bunched together, and the spacing between the bunch-air cavity and the catch-air cavity has to be adjusted in such a way that this Td is equal to T3 minus T2, where the Td is calculated by the equation L divided by u into T2. So this is equal to T0 into 1 minus m by 2 into sine of omega T2 minus theta g divided by 2. Okay. If this particular condition is satisfied, so then we are getting the maximum bunching. Now, continues with the density modulations, where the T naught equal to L divided U naught is the transit time in the drift space. That is, transit time in the drift space means how much amount of the electrons, time the electrons will take to move from buncher cavity to the catcher cavity. Then the corresponding transmit angle in the drift space is calculated from these particular equations, where theta naught is equal to omega T0 is the DC transit angles. Remember, this is the equation which you are using to calculate the transit angle, and this is the equation which is going to give the transit time. And once the electrons are bunched together, then the bunched beam current we are getting. So the bunched beam current is calculated from this particular equations, and where this J1 of Nx, whatever this terms, new term we are getting, this particular term is taken from the Bessel's functions table. Okay? And you are not supposed to bother about the derivation of all these particular equations, just remember this particular equation. The bunched beam current is calculated from this equation, where this J1 of Nx value will be taken from the Bessel's function tables. Then the fundamental component of the current is maximum for an output to drift space length. Okay? Now, the fundamental component of the current is maximum. That means when the current is going to be maximum, okay, that current is going to be maximum for an optimum drift space. That is, L optimum is equal to 0.3682 U0 into V0 divided by omega into B1 into V1. When we are getting these particular values, then we are getting the maximum fundamental component of the current. Then, the power output, the average power delivered to the cavity output is calculated from P0 is equal to beta 2 into I0 into V2 into J1 of x cos of I. Here once again, whatever this particular J1 of x you are getting, this value is taken from the Bessel's function table, and this beta, what it has been shown, it is a coupling coefficient. If you want to have a maximum power output, okay, for maximum power output, cos phi is equal to 1, therefore phi is equal to 0 and x is equal to 1.841. So this x is equal to 1.841. So here what are the x we are having here? So these values, this x is equal to 1.841 will be taken from the Bessel's function table, and you want to have a maximum power output, x must be equal to 1.84 and coupling coefficient beta 2 must be equal to 1. So therefore the maximum power output is calculated from I0 into V2 into J1 of x. So this is equal to 0.582 into I0 into V2. So that is this 0.582 into I0 into V2. So it is going to give the maximum power output. Efficiency is calculated from the formula efficiency equal to RF output power divided by DC beam power. So that is efficiency equal to PAC divided by PDC. PDC is calculated, PAC is calculated from this equation, and PDC is calculated from these equations. Okay, and the efficiency is going to be maximum when the values of x is equal to 1.841, and this value of x is equal to 1.841. We are taking it from the Bessel's functions. Now maximum efficiency is equal to 0.582 into beta 2 into V2 divided by V zeros. And if the coupling coefficient, if the coupling is perfect, that is coupling coefficient beta 2 is equal to 1, then the maximum current is equal to 2I0 into 0.582 and V2 is equal to V0, then the maximum efficiency is equal to 58.2. So that means to say that, this two cavity klystron amplifier is having a maximum efficiency of 58.2%. Okay, if the coupling is perfect, that is if the beta 2 value is equal to 1, that means in this equation or in this equation. Okay, here if the values of this beta 2 equal to 1, so then the current is, you are going to get it as 2 I naught onto 5.582, and at that particular time V0 equal to V2, then efficiency is going to be 58.2. The voltage gain is calculated from the equation AV equal to V2 divided by V1, and the voltage gain AV is equal to V2 is calculated from beta square theta 0 V0 into J1 of x and x into V0 into GSH, and B1 that is coupling coefficient B1 is equal to B rho for identical cavities. B1 equal to B2 for identical cavities means you have the two cavities, one is a buncher cavity and the other one is the catcher cavities, and B1 is the coupling coefficient of the buncher cavity and B2 is the coupling coefficient of the catcher cavities. For the identical case, the coupling coefficient of the buncher cavity and the catcher cavity has to be same or equal. So, therefore, B1 equal to B2 has been taken. Then mutual conductance of this particular reflect crystalline is represented by Gm. It is equal to IC divided by V1. It is calculated from this particular equations. And you have to remember this particular equation, no need to bother about how these particular equations have been derived, and therefore gain equal to Gm divided by GSS, and for the maximum power output, because X is equal to 1.841, then Gm equal to 0.136 into G0 into B square into theta 0.